Hello everyone, my name is Kevin Okansi. For my final year project, I built a chess engine using convolutional neural networks. Unlike the state-of-the-art engines like AlphaZero that are based on reinforcement learning, mine is a supervised engine with the goal of transparency. I wanted to understand what is happening within the network when the model makes a prediction. To do this, I explored three models, VG16, ResNet-50, and DenseNet-121. My presentation is going to cover a bit of history. I'll look at past engines like Deep Blue, which worked perfectly with somewhat transparency and interpretability. Then I'll move on to the current state of the art like AlphaZero, which uses reinforcement learning, and talk a bit about neural networks. Then with that information, I'll lean into my project aim and objectives, and then I'll touch a bit about the different methods and what's instructed each choice, starting with input encoding, the different deep learning models and why I chose them, XAI technique. Then I'll talk about my artifacts and results and end with discussion and conclusion. In 1997, IBM's Deep Blue defeated Garry Kasparov. Its strengths came from four main components. It had custom chess chips, specialized hardware for evaluation, improved search software, and an extended opening book. So basically, how it worked was it encoded thousands of human chess concepts like material, mobility, king safety, and maybe many of them were helped developed by a grandmaster called Joel Benjamin. So, given a particular position, it would scan the board to score each of these chess concepts and then add them all together. And to predict a move, it does a similar thing by looking through the search tree and figuring out, based on these concepts, which position is the best. AlphaZero, on the other hand, teaches itself to play the game of chess. It uses a deep neural network with Monte Carlo search tree. So after each game it plays against itself, it updates the neural network, the weights, and also the evaluation function. The updated network is then tested again with another game against itself. And if there is a better player in the pool of players that it has played against itself, it chooses that player as the best and then keeps playing itself. This allows AlphaZero to improve very quickly. Now, neural networks are built from layers of nodes. Now, each node learns to focus on different aspects of the data. So, information will be passed from these nodes to different layers as it moves on. And each layer can learn simple things to more complex stuff. So for example, neural networks were first designed for images, and they were first able to identify edges, then shapes, and then to full objects, and able to classify different objects. But as they learn, they are basically updating the weights within themselves and the biases. Um, and this learning pattern is difficult to translate to human ideas and concepts. This makes neural networks a black box because they are very good. However, do not understand what they've learned and why they make a prediction. This is the main issue that my project tries to tackle. We have different architectures and different neural networks, and the goal is to try and figure out which ones are very suitable for explainability techniques and what type of explainability, how different do they express these techniques, like how different do they react to these different explainability techniques. So the aim is to train and evaluate multiple deep neural network using Lichess data. Lichess is an open database for chess games. Then we are going to define some human understandable chess concepts to facilitate the inspection of these deep these models and figure out how what chess concepts are closely correlated to move predictions. And after that we are going to apply some interpretability methods tailored for CNN, um, like saliency maps. And then we are going to review their results. So one interesting thing to think about when dealing with neural networks is the input representation. So as I said, they were first designed for images. Now images are basically pixels with a width and a height. And these pixels have different channels, that is red, green, and blue. Chess is kind of similar to an image. A chessboard is kind of similar to an image, where the width could be the 8 by the width and height is basically the 8 by 8 because, and the channels in this case could be either algebraic or a bitmap. So with the algebraic, we just need one channel where we represent each square by what piece is sitting on that square. For pawns, we can represent the piece by 1, for knights by 2, for bishops by 3. For bitmap, on the other hand, we can have different layers to represent different pieces. What that does is that it gives us the opportunity to also add concepts as a layer. So we can have one layer representing en passant, which is a concept we are looking for on the board. We can have another layer looking for king safety on the board. And that could be represented by 1, 0, or -1. Where 1 could be for the white pieces, 0 could be there's no piece or concept existing, and then -1 could be for the black pieces. When it comes to deep learning models, the one I'm going to focus on for now is DenseNet and ResNet because they were the ones that achieved the highest performance. Now, ResNet works a bit differently because at some points within the layers, it can send the information to, let's say, the third or fifth layer by skipping. The reason is that models can learn pretty quickly in the first 2 or 3 layers. But when we skip, we can also preserve some information to be sent to the next layers. DenseNet, on the other hand, connects all the layers together. So you can have fewer layers, but we can make sure that all the nodes in the layers are deeply connected. This makes it efficient. XAI techniques that we explored were saliency maps, SHAP, and TCAV. Saliency map basically is basically pointing out where the model is focusing on the image, or in this case on the chessboard. Text concept activation vectors are basically saying that we are going to create a concept and we are going to see how much this concept, when we put off that concept or put it on, how much does it influence the model's behavior. So our best models were ResNet-50 with the 19 plane, and then ResNet again with the 12 plane, and DenseNet with the 19 plane. Those are our top 3 models. Top 1 accuracy basically is we compare this to a benchmark model called Stockfish, and Stockfish predicts the best move given a position. And we are saying that for each of these models, ResNet ResNet scores 30% as much as Stockfish. So at any for each for a given position, ResNet can predict the same move that Stockfish predicts 30% of the time. But if you are talking about the top 5 moves, it can predict up to 60%. In terms of efficiency, DenseNet was the most efficient because it has fewer parameters, and then followed by ResNet, which has 25, but VGG was most wasteful because it had a lot of parameters but less accurate. So we had different types of visual techniques like integrated gradients and saliency maps. With integrated gradients, it was more clear that we could see that ResNet's family, both the 12 plane and the 19 plane, showed similar parts of the board when it makes a prediction given a particular position. But when we use saliency map, it was harder to figure out because the heat map was very scattered across the board. But with integrated gradients, it was more clear which exact, it could pinpoint which exact board um, box or square it was looking at. SHAP, on the other hand, what it does is that it shows where the model is looking. So SHAP tells us which feature actually drives a prediction. So we've already encoded features like kin safety, mobility ratio, and all these. And we could see that these ones had a higher either positive or negative, showing its contribution, how that concept contributes to a model's output. TCAV takes SHAP to one step further. So instead of just looking at the features, it asks whether the network has actually learned these human chess concepts. So first we define the concepts, then we search through the games to find how many of these positions does this concept appear. So using those positions, we probe the model to activate the concept. So if activating the concept significantly changes the prediction, it means that that model has learned that concept. If it doesn't, then it means that the model has not. So when we did this, we found out that the 19 plane model captured these concepts much better than the 12 plane model. To conclude, it shows how we can balance interpretability with predictive power. With more techniques, we can increase predictive power, but then we can also um, expand how we translate these concepts. The only issue is that the concepts we are the concepts we are using to test these techniques and these models are human concepts. So we cannot actually know what new concept that the model has learned directly. So that's the only drawback. But this project can extend further into something more, something with more human language if we attach an LLM. But it also shows that the different architectures shape interpretability. So that's also something we can explore later in future works. And the last thing is that this project focused on just move prediction for one given state, but we can also explore how the engine learns 3, 4, 5, 6 moves ahead because those are more complex things to investigate. So thank you for this opportunity.